All right, here we are, 1.1 day number 2. Doing some more review of functions. Today we're going to talk about secant lines, difference quotient, symmetry, which relates directly to even and odd functions. So let's go ahead and look at secant line and difference quotient. So a line through any 2 points on a curve is called a secant line. The slope of the secant line through these 2 points is given by, well, our slope equation. There's 2 main ways for us to express the slope formula of a secant line. We're going to look at both of those right now. Let's look at the first one, and then the second one we'll look at on the next page. Okay, so here we go. We're going to put a point P and a point Q on this graph, and we're going to go from there and develop this thing called the difference quotient. So let's go point P here, and it looks like point P has an x value of x and a y value of f of x. So point P is the point x comma f of x. So there's its x and its y value. All right, we have another point Q here, and it looks like we're going to add some arbitrary value to x. So this would be f of x plus h, its y value. So this point here would be x plus h comma f of x plus h. Okay, we're going to develop this thing called the difference quotient. So the slope of the secant line, so rudely interrupted, the slope, slope, yeah, it makes sense, of a secant line is going to be the change in y over the change in x. So let's look at our 2 y values. Well, let's take f of x plus h, that's our y value at one point, point Q, minus f of x, which is our output or y value at the other point, divided by the change in x, which is x plus h minus x. Okay, so if we simplify this, I can't do a whole lot in the numerator, at least yet, until we get a function that's given to us. So we're just going to leave that as is. F of x plus h minus f of x are 2 y values. But down here, what's cool is going to happen is the x's are going to go away, and we're left with h. And there is our first definition, which is called the difference quotient. I can't spell. Difference quotient. That's our first form of the difference quotient. Now, just interpreting this, the slope of the secant line in this form is interpreted as the average rate of change over that interval x to x plus h. So it is the average rate of change. So let's look at that for a moment. So of all the slopes along this curve, that is the average slope on that interval. All right, let's look at the other alternate form. Okay, so now we're going to generalize this in a little bit different way. We're still going to have P over here, and we'll call that now x and f of x, no change there. Whoops, sorry, I got that backwards, my bad. We're going to call that a and f of a. So the point P is a comma f of a. This will come in handy later on. You'll see, you won't see probably this chapter, but later on in limits, and then for sure in derivatives as well. And then this point Q, which is located at x comma f of x. Okay, that'll be x comma f of x. And then the difference quotient will be formed yet again in a different way, well, the same way with a different form. So we would have f of x minus f of a over x minus a. Now we can't simplify that any yet, but we'll have some situations later on where we can. Again, interpretation, the slope of the secant line in this form is interpreted as the average rate of change from a to x. So if I were to draw a segment from point P to point Q, the slope of that is the average rate of change on that interval. Okay, so let's find the slope of the secant line for f of x equals x squared over this interval from 2 to 3. Okay, so the slope of the secant line is going to equal f of x plus h minus f of x all over h. Now what is h? H was the change, right, on our graph, right, from P to Q. h was this value. Right? What is this value? Well, that value was f of x plus h minus f of x. So let's do a little bit here and figure out what's going on. Okay, so f of x plus h, well, that's just going to be our input here, our output at q. Okay, this is our output at q. This is our y value at q. Well, our y value at q would be whatever our output is for f of 3. What would our y value be at p? Well, that would be whatever our output is when x equals 2. And h is the change. Well, what is the change? The change is 3 minus 2, which is 1. So let's do f of 3 minus f of 2 over 1. F of 3, well, that's 3 squared minus f of 2, well, that's 2 squared over 1 would be 9 minus 4 over 1. So it looks like our average slope, from here to here is going to be 5. Okay, so let's move on to another example. Example 2. Okay, we're going to simplify in general terms the difference quotient for f of x equals x squared. So for a second, f of x plus h. Well, what would f of x plus h equal? Well, that would, instead of x squared, I'm going to plug in x plus h. So that would be, FOIL it, x squared plus 2xh plus h squared. What is f of x? Well, f of x is x squared. So in the difference quotient in the numerator, if I have f of x plus h minus f of x over h, that's going to be the same as, okay, f of x plus h. I know what that is. That's this. And f of x, well, that's this. So if I take x squared plus 2xh, h plus h squared, and I subtract x squared from that, and I divide all that by h, we're going to get something that's going to lead us eventually to the derivative. We won't get there yet, but the x squareds will cancel. I'll get 2xh plus h squared all over h. And what do all of those combine? All of those terms, each term, one term, two term, and that term, what do they all have in common? They have an h in common. So the h cancels out of all of them, and what we're left with is 2x plus h. That would be the simplified version of the difference quotient in general terms for x squared. Okay, so we got this 2x plus h thing. Let's find the slope of the secant line for f of x equals x squared over this interval from 2 to 3 using the difference quotient from example 2. So we found that the difference quotient is 2x plus h. Well, what is x? Right? And what is h? Because if we know what x is and what h is, we can plug them in directly here, and we should get the slope, right? Because the difference quotient gives us that. Well, recall when I did the general terms earlier, and I went p and I went q, and I called this thing a, I called that a and I called this x. Well, in this case, I have a 2 and I have a 3. So a is 2 and x is 3. So I know x is 3, but what is h? Well, h is the change between those two, changed by 1. So it looks like h is 1 and x is 3. So when I plug that into this difference quotient, I'd have 2 times x plus h. So I have 2 times 3. Uh-oh, I got a problem. Okay, so my mistake here, the x value that I started at was 2, which we already know, and then it changed by 1 to get to 3. So my x value here should be a 2. And then, of course, h is still 1. So 2 times 2 is 4, plus 1 is 5. So the slope on that interval, right, which we looked at on the previous page right here, ended up being 5. Well, when I use the difference quotient, same thing happens, right? Okay, so we've confirmed it using the difference quotient that that slope also comes out to be 5. Okay, so we got some work to do on this next example, example 4. We're going to use a special property called the conjugate, which you'll see in just a minute, which is going to help us to do a little bit of work on that. Okay, so I went ahead and I wrote out this alternate form of the difference quotient using our function f of x and then plugging a in for f of a. Okay, so I get this rational expression. Okay, now a lot of times something that is going to be a nice friend of ours is going to be this thing called the conjugate. So I'm going to multiply the top and the bottom of this rational expression by the conjugate of the numerator. So it's the same thing as the numerator except one change. I'm going to change this negative symbol in my conjugate to a positive sign. Okay, and then we're going to go ahead and, uh-oh, I did something wrong. No, there, we're good, we're good. Okay, so I'm going to go ahead and FOIL. Now, the nice thing about the conjugate is that you don't have to do the complete systematic foiling process because those outside and inside terms will cancel. So as I FOIL, if I have conjugates, I can just scratch those outside inside terms because they'll cancel each other. So I just have to go first times first and last times last. So that times that, if I take the square root of something times itself, I just get that something that's inside that radical. Okay, likewise, if I do these two terms multiplied together, of course, I'm going to get the same thing except I'll get minus, right? That negative symbol right there travels along with it, and I'll get a squared plus 1. Okay, in the denominator, I'm not going to try to do any sort of work. I'm just going to leave it as is. And you're going to see something relatively nice. It won't be all that pleasing at the end, but you'll see something relatively nice come out of this in the end. Okay, so let's simplify the numerator. Looks like the 1's will cancel. It doesn't look like anything's going to change there, but I get this. And that right there, x squared minus a squared, should start to maybe ring a bit of a bell as it's a difference of perfect squares. Okay, so let's take a look at what's going to happen here. If I had x squared minus 9, that would mean I'd have x minus 3 and x plus 3. So if I had x squared minus a squared, that would mean I have x plus a, x minus a. Doesn't matter the order in which I have those. So technically speaking, my numerator is x minus a times x plus a. And conveniently, what you'll see is that these x minus a's, they're going to cancel. And so I get a somewhat simplified version. And the difference quotient comes out to give me x plus a over the square root of x squared plus 1 plus the square root of a squared plus 1. Now, right now, since it's in such general terms, it doesn't necessarily please the eye, but it will later on. Okay, let's keep moving. Let's talk about even-odd functions. Okay, even-odd functions are symmetric with respect to the y-axis. Okay, so let's look at one, a general one. Here is your function f of x equals x squared. So on f of x equals x squared, let's say this is 2, then this point would be 2, 4. What's true about even functions is that if I plug in a negative 2, I still get out that same positive output, or negative output, depending. So what's true about even functions is that f of negative x has the same output value as f of x. Okay, that's the definition right there of an even function. Symmetric about the y-axis. Okay, odd functions are symmetric with respect to the origin. Example, how about the sine function? Okay, f of x equals sine x. Well, let's go here at pi over 2. Well, if I plug in a pi over 2 into sine of x, I get a 1 out. What happens if I plug in a negative pi over 2? If I plug in a negative pi over 2, I get a negative 1. So in order for a function to be odd, f of negative x has to equal the opposite of f of x. Okay, so let's prove algebraically whether or not x to the fourth is odd, even, or neither. The first one I typically try to prove is even because it's the simplest, right? If the function is even, then f of negative x should equal f of x. So what is f of x? F of x is x to the fourth. What is f of negative x? Well, f of negative x would be negative x to the fourth. And what happens is, and when I square a negative, or take a negative to the fourth power, checks. That's an even function. All right, let's check another one. Odd, even, or neither. So let's check to see if it's even first. So f of x equals, I think that's x cubed over x squared minus 1. X cubed equals x squared over x squared minus 1. So let's take f of negative x and see if it's equal to f of x. Okay, so I have x cubed over x squared minus 1. If I plug a negative x in, simplify, nothing's going to change over here on the right. Over here, I'm going to get negative x cubed over x squared minus 1. Right there, they're not equal, therefore it's not even. The next step I would take with this is take your function, f of negative x, and pull out a negative 1. That's x cubed, and I get x squared minus 1. If I pull out a negative 1, is f of negative x equal to negative f of x? Well, what would negative f of x be? Well, x cubed over x squared minus 1 is f of x. If I made that negative, look at that, they're equal, so that's an odd function. All right, let's move on. Determine whether the following function is even, odd, or neither. You're probably like, oh, it's going to be neither, and you're right, but let's confirm it. So let's see if f of negative x equals f of x. I'm not rewriting the right side. We already know what it's supposed to be. If I plug in a negative x, am I going to get the original function? Well, this would be x to the fourth. That checks, right? But this will be a positive x cubed. That doesn't check. Okay, so I know right now it's not going to be equal to f of x. Okay, I could just toss the plus 2 on the end to prove it, blah, blah, blah. Not even. Not even. Okay, let's check to see if it's odd. What if I pulled out a negative 1? If I pulled out a negative 1, that'd be negative x to the fourth minus x cubed minus 2. Okay, so that's f of negative x. Is that equal to negative f of x? Well, negative, let's see, what's f of x? X to the fourth minus x cubed plus 2. I mean, there's obvious contradictions here. That's not true. That's not true. Those aren't equal, so it's not odd. Therefore, it is neither. All right, let's do a little table representation here with composite functions as well as even odd. Okay, so what I like to do on these, first of all, is I like to toss negative 1. Oh, I don't have enough space. Let me move this over. Okay, I like to duplicate my table over here. Okay, so I'm going to put a negative 1 there, a negative 2, a negative 3, a negative 4. It just makes visualizing this a little bit easier. So it looks like f is even. So f of 1 and negative 1 are going to be the same. F of 2 and negative 2 are going to be the same. F of 3 and negative 3 are going to be the same. F of 4 and negative 4 are going to be the same. Okay, g is odd. That tells me that all the outputs for g of x are going to be the opposite sign when you change the x value to its opposite sign. So g of 1 is negative 5. G of negative 1 would be positive 5. That would make this negative 2. That would make that negative 4. That would make that negative 3. Okay, so now we're ready to do some work. Of course, we haven't talked about 0. We'll talk about that in a minute for both of those. Okay, so g of f of negative 2. So what is f of negative 2? Well, according to my table, it's going to be 3. And what would g of 3 be? Well, we could check our table over here. It looks like g of 3 would be 4. Okay, now here comes something kind of interesting, right? What is g of 0? And I didn't talk about this earlier, but every odd function, not every odd, I shouldn't say that. Yes, every odd function, that's true, has to go through a specific point. It's symmetrical about the origin. All right, so it's got to go through 0, 0. So g of 0 has to be 0. So we're taking f of 0 plus 2, which is the same as f of 2. And when I look at my table up here, looks like f of 2 equals 3. So there you have it. That's 1.1, day number 2. Like, subscribe, comment below. GNC gift card to Mr. Dama.